Welcome back to Office Hours with Dr. Clark. So we're going to be covering alkene addition reactions today. So on another video, I went through the alkene addition reactions that involve mechanisms. So I'm not done doing the mechanisms during this video. You can look at the other video to see the mechanisms that you should, the basic ones that you should know. So there are quite a few alkene addition reactions that we cover in Orgo 1. Alkenes are very versatile, so there's many reactions that involve them that are outside the scope of the course. But the first one that we always address is hydrohalogenation. Kind of a tongue twister there. So we're gonna look at HBr, It's a Markovnikov addition. Remember, Markovnikov uh, means that the Br, the halogen, ends up on a more substituted carbon. So let's use one bromo, excuse me, one butene and HCl. Product is 2-chlorobutane, and we can form stereoisomers because carbocation, if you recall from the previous video, it's a planar molecule, so the chloride, which attacks, can attack from above or below. Okay. The other one is the anti-Markovnikov hydrohalogenation, and this one only occurs with HBr. So I use the same one, butane, and I'm going to use HBr, and I'm going to put some peroxide in there, and we're going to get the Br on the less substituted carbon. So that's an anti-Markovnikov hydrohalogenation. Acid catalyzed hydration. So now that number two, that mechanism is a mechanism that we will cover in a later video, but that falls under the free radicals. Acid catalyzed hydration. There's three of these. So let's kind of use, there is sorry. There are three hydration reactions. One is called acid catalyzed, so then there's kind of like hydration. All right. So let's call it number three, just for clarity's sake. So the first one is acid catalyzed hydration, H3O plus. We end up with an alcohol, 2-butanol in this case, plus an enantiomer, because still this one is a carbocation intermediate. Right? Right? And we covered this mechanism in the previous video. And then there is the oxy mercuration, demercuration. So acid catalyzed hydration, there's a carbocation intermediate. And as we always talk about, carbocations can rearrange, and sometimes you don't want rearranged products. Well, oxymercuration, demercuration, there's no carbocation intermediates, and we won't go through the mechanism. It's a little more complicated outside the scope. But we use mercury acetate, so always use acetate if you recall, and we use H2O as the first step of the reaction. Then the second step, we use sodium borohydride, which actually is a reducing agent. And you'll see that sodium borohydride that we'll go to. But you get the Markovnikov addition of the OH, and it can actually have stereoisomers as well. And the mechanism would it's actually it's a three-membered ring that's formed as an intermediate, so you can have addition above or below. But don't worry about that mechanism. Just know it is Markovnikov, and it avoids rearrangements. That's why it would be used. Now, the fact that you have mercury as one of the reagents makes it not something that you necessarily want to use on an industrial scale because mercury is very toxic. And then the last one is a anti-Markovnikov hydration, and this is hydroboration oxidation. So there are a few that we got to think about. So, and this is pH3. Now we use THF, which actually helps the reaction go better. And I'll show you what THF stands for. It's a very common solvent. It's a cyclic ether, actually. Those two. So the second step is sodium hydroxide and hydrogen peroxide. So THF looks like this. It's called tetrahydrofuran. And then you get an OH on the less substituted carbon, right? So three hydrations. You have one that's anti-Markovnikov, one that's Markovnikov, but no rearrangement. And this one doesn't have a carbocation intermediate either, so no rearrangements. This one avoids rearrangement. It's Markovnikov, and acid catalyzed hydration has a carbocation intermediate, is Markovnikov, and can rearrange. Next one is halogenation. Halogenation, that'll be next on the list here. So halogenation, CO2, Br2. I'm going to use a ring this time. Make a point. So if I use CO2, and I've covered the mechanism for halogenation already in another video. I just wanted to just go through reagents and reactions and any kind of stereochemistry and regiochemistry in this video. So your halogenation, notice that the chlorines are trans to each other, and we can get enantiomers as well. And the same thing would happen with bromine. Now, a related reaction is the halohydrin formation. Let's use the same molecule. I'm going to use Br2 this time, and I'm going to use H2O as a reagent, as well as a solvent. And I'm going to have an OH on the more substituted carbon and a halogen on the less substituted carbon. So this is actually a Markovnikov addition. So neither of these involve any rearrangements because they don't involve a carbocation. There is I could draw the intermediate that's formed that a lot of students struggle with this intermediate because it looks kind of strange. It's positively charged three-membered chlorine ring called a chloronium. Chloronium ion. Right? So the intermediate, so that's not a carbocation, so there's no rearrangements. And this would form a bromonium intermediate, just like the chloronium. All right, so no rearrangements here, but Markovnikov, and you can form stereoisomers, either enantiomers or diastereomers. Let's look at hydrogenation. Hydrogenation is very practical because we use that when we're hydrogenating oils and fats to make spreads like margarine. Think about hydrogenation. I'm going to use a cyclic alkene to make a point here. It's H2. And I could use platinum or palladium, nickel, or rhodium. Those are the classic ones. There's some newfangled ones now that can give you some stereo specificity with your product, so we're not gonna worry about those. So look at what happens here. So this is my product. Um, so I get a cis, so we'll call this syn addition. Syn addition. So my hydrogens add on the same side of the molecule. Could be the top side or the bottom side, right? So you can get stereoisomers. Now this wouldn't give me an enantiomer. Why would not this molecule give me an enantiomer? So pause and think about it. Exactly, because this molecule, though it has chiral carbons, it's the line of symmetry. So this is meso, right? So there are no enantiomers. But I will not form the trans version of this because the hydrogen only adds to the same side. That's hydrogenation. Let's look at syn dihydroxylation. There's a lot of reactions with the alkene additions. So there are two, so I'm going to use and do a cyclic again here. So I could use osmium tetroxide, and I'm going to end up with a diol. I can get an enantiomers there too, right? Because I could add either above or below the molecule, but the OHs will add in the same side. Right? Or we could do the same reaction with cold potassium permanganates under basic conditions. I will get the same thing. Right, so that's syn addition. There's no Markovnikov here because we're adding the same thing. There is well, actually, let me let's, let's talk about epoxidation first. Epoxidation. So epoxidation, I form something really cool. So I use a peroxy acid and I get an epoxide. And I can form an enantiomer here too, because epoxide can add below or above the plane of the molecule. So an example of epoxide peroxide is MCPBA, which is metal chloral peroxy benzoic acid. So peroxy acid has this is a generic peroxy acid. It looks like an acid as well as a peroxide. That's why I call it peroxy acid. Yeah. And this is a mechanism you don't have to worry about. It's actually kind of cool concerted mechanism how the oxygen ends up on both carbons. But if we take this peroxy acid, we can actually make something else. We can do anti-dihydroxylation. So it's typically where a two-step thing. So MCPBA forms a peroxide, and then we add acid, dilute acid, and we end up with a trans diol, and we can form enantiomers there as well. So that's what we call anti-dihydroxylation, two-step process. Form the epoxide and then follow that with dilute acid. So we're coming down to the end here. The last one is oxidative cleavage. Oxidative cleavage. So when you think of cleavage, you think of where we're splitting the double bond in half. So for example, let's take this double bond. There are two hydrogens. I'll draw these in on purpose. I'm going to use ozone. So we so an example of oxidative cleavage. There are others, but ozonolysis is an example of oxidative cleavage. So use ozone followed by zinc. Okay. So the zinc is a reducing agent, but you can use other reducing agents as well. Uh, and what happens, we clip the double bond in half, and if there are if R groups on double bond, you form a ketone. If you have any kind of hydrogen, you're going to form an aldehyde. So this reaction is not really useful for making aldehydes and ketones, right? We have way more efficient ways of doing that using alcohols, for example. But in olden days, it was a good way to elucidate the structure of your double bond, right? So, for example, if I did a reaction and I formed an ozonolysis and I formed this aldehyde and I formed this ketone, right? Or some alkene, and I did O3 and zinc, and I got these. So what I do is I just put the I just put the double bond oxygens together, and that's going to give me the framework for my molecule, my alkene. Okay. So you have one, two, three, four, five, six, seven, so seven chain alkene. So it's a heptene. So I'll say it's 3-methyl 3-heptene, alkene. So that's the usefulness of ozonolysis. With ozonolysis, if you form, let's take another example. So I form only one product. That means my alkene was symmetrical. If I did ozonolysis, here's my alkene, X alkene, did ozonolysis. Sometimes we can write the arrow going in the opposite direction, right? Um, Even though most people think, left to right with reactions, but we're allowed to. So I will just put, both. This is acetone, by the way. Both of those together, and then so the alkene looked like this. Because when we split it, we got the same thing. So therefore it's symmetrical. So those are our alkene reactions. So a good thing to do with these is what I call a starburst. They say it's right, so H2, palladium, for example, hydronium, ACL, RCO3H, followed by, call that A, followed by hydronium, give me B. And just kind of keep going, CO2, Br2, and H2O. And try to figure out. So every time you're studying, you're just drawing putting a new alkene in the middle, and you're gonna say, okay, well, I'm gonna get alkane here. I'm gonna get an OH here. You're gonna give me HCl. I'm sorry, alkyl chloride. This first step here, give me epoxide, then follow up. I'm gonna get a diol. It's gonna be an anti one. And this is gonna give me an anti-chlorine addition. This is gonna give me halohydrin with the OH on a more substituted carbon. All right. So I'm just filling this out. And there's more. I didn't do like a also analysis or a sin, but you get the idea. And then also you can draw some tables, right? You could say, all right, what are some reagents? So we know we're dealing with alkenes. If I have HCl, the regiochem is gonna be Mark. And a stereo, yes, I could get enantiomers or diastereomers. Products, get so let's actually let me back up here. So alkene. So let's take a propene again. The product is gonna be chloropropane. Um, and so you can make like a little table so you can list like all the hydro and you can and then name, so they call this hydrohalogenation. Because sometimes students they know the reagents and they know the products, but they don't know the name. And something that could throw you off on a test question. They said, oh, perform a hydrohalogenation reaction using protein, using HCl. You're like, what is hydrohalogenation? Um, but if we were to show you, a problem with, you know, say butene and HCl, you immediately know, oh, yeah, well, that's my product. If we say halogenation, then you may not necessarily, understand what the product is. All right. So that's our alkene reactions or, basic alkene reactions for Orgo 1. And we'll see you next time. Officer Dr. Clark. Take care.